So what we are looking at here is a hot plate with a beaker of water and two test tubes that have, the pink one has alcohol in it, the blue one has water, and the food coloring just adds a little dimension so that way we can see our solutions clearly in the tubes. And we have two open glass tubes here. And through this process, we're going to use the hot plate to heat these solutions. Through our discussions in class, we have decided that particles can only transfer energy through contact, through hitting collisions, and that's how we pass across energy. And in this case, energy in the form of heat or speed of the particles. Since the hot plate is not in direct contact with our alcohol or water solutions, we have quite a few transfers that happen between the hot plate and our solution. So first, what's going on in the hot plate, these particles are getting really fast because they're getting very hot. And as they speed up, they collide and transfer some energy to the particles of the beaker. Those particles, since they have more energy, start to move faster and bump into each other, and they come in contact with the water at the bottom of our beaker or along the sides and give off some energy to the water. That causes the water to move faster. The water particles move faster and transfer that energy to other water particles and to the particles that are in the glass tubing that we have here. So the glass tubing can start to move faster and transfer that energy into the particles that are inside of them, the solutions of alcohol and water, to make them move faster, and in turn turning up their temperature or giving them more heat. So the transfer is really the hot plate to the beaker, to the water, to the glass of the test tubes, to the solutions inside, and each time we're making those particles move faster. Now the movement of these particles in the hot plate is, they're in a solid, so they're kind of sitting there shaking back and forth. That's the same with the beaker. Those solid particles are staying in place, they're just shaking faster. Once we get into the water, those particles can really move around a lot more being in the liquid state. And then back to shaking particles in the glass of the test tubes, but the liquids inside of the test tubes, since they're liquid, they get to move a lot faster. So as we are doing this, we see that the solutions have started to creep up our glass tubes. So we can see at a pause here, our water has increased and our alcohol has increased up the tube. So we look at this and say that the liquid has expanded. And I know that we talk about not using the term expanded when we speak of particles, because referring to a particle expanding means making it bigger or giving it more mass. And that's just not possible because mass can't be created or destroyed. We can't magically just put more mass into a particle. So we say that the particles spread out. But when we talk about a solution or an object, we can say that it expands because we're looking at the system as a whole and all of the particles. So that level of solution is expanding. And the real question is, why is it expanding? So as those particles in the alcohol and the water heat up, they start moving faster. So they have more energy, they're moving faster, they need more space. And with that, they make more space by pushing the level and the solution away from each other and spreading out. So we see this increase. And If I zoom back just a little bit, we can see that we're really getting quite a bit of height up here from our initial position. So we're really, these liquids really are heating up and spreading out. So, so the expansion of this liquid is being caused by those particles moving faster and needing more space, taking up more space. So one question to ask is, compared to the cooler solutions, what do we see in terms of density? So the density of these that are hot and what they were before when they were cold. Well, the density has definitely decreased because we haven't changed the amount of mass here, but we've changed the amount of volume. We've given it more volume. So we have the same mass, more volume, and density is the mass in that volume. So we have a lower density at this point when they're hot. So hotter solutions have a lower density because they take up more space but have the same amount of mass than before they were heated. The other thing that we ask is, this is going on for liquids. We can look at this in terms of gases, and we know that through, these particles will move faster. So it is not a huge leap to say that a gas will expand when we change the temperature. When we increase the temperature, we can see the gas increase. Now, the tricky part is when we talk about solids, because looking at solids, it doesn't really seem that they expand when we heat them up, but their particles are still moving faster. So that vibration, instead of vibrating back and forth like this, they vibrate like this, and they do get a little bit more motion into them, so we see some slight expansion there. If you've ever been inside of a barn or anything with a metal roof in the summer when it's really getting hot, you'll hear the creaks and groans of that roofing, and it is the metal expanding. So that solid roof is stretching, it is expanding in there. Okay, the last thing, and now that we really have quite a few little marks, we've got some temperature going in here. We want to look at why the alcohol is so much more expanded than the water. And one theory is that in the alcohol, since it is less dense, there are less particles to heat up, whereas in the water, there's more particles, so there's more to heat up. I am giving both in this water bath. They're both getting the same amount of energy. They're in the same depth, so I'm essentially handing over the same amount of energy into both test tubes. So why does the alcohol get so much higher than our water solution? Well, since I'm handing the same energy, we can talk in terms of money instead of energy, because money is a little bit easier to understand. So it's like if I had 30 people in a classroom and I gave the classroom $500, that would have to be divided up amongst 30 people. Whereas if I had a small group, like 5 or 6 people, and I gave them the same amount of money, the same $500, dividing that up, each person in the group would get more money than each person in the class. So looking at this, the particles here in the alcohol will get more of the energy because there's less particles in here to share. Whereas the water particles, there are more particles here, so they have to split that energy between all of the water particles versus the alcohol, who have less particles to do the sharing. So that's kind of where we see this. That's one real theory here. The question becomes temperatures of these two solutions, because temperature, we've decided, is speed. Okay, hot things are fast, cold things are slow. What would you assume if each of these particles in the alcohol get more energy than each particle in the water? What would you assume about their speed? Well, we think that they should be moving faster in the alcohol. So there should be a slightly different temperature in the alcohol versus the water. But it would take extremely precise temperature readings and thermometers to be able to detect the difference between both of these. Certainly more precise than what we have here. So that's really what we want to get out of this demonstration, is the transfer of energy from the solid hot plate to the beaker, to the water, to the glass tube, to the alcohol inside of the tube. And then also this expansion, this idea of expansion, where particles move faster, so they need more space, and they expand, and we see that solids, liquids, and gases all do this expansion. And then we can also compare two different solutions. We can see that the alcohol, because it is less dense, does expand at a different rate than the water, which is more dense.